Hello, and welcome to Dr. Vaughan's Philosophy 101 online lectures. This is part 2 of Lecture 3 from the Epistemology Unit, the historical context of the modern period, the Renaissance, and the rise of skepticism. Lecture 3 is designed to provide you with an historical context for reading Rene Descartes' Meditations on First Philosophy. In these lectures, we'll examine the social, political, and intellectual transformations that occurred during the Renaissance. We'll give special attention to 3 intellectual revolutions that occurred: the scientific revolution, the geographical revolution, and the theological revolution. The outline for Lecture 3 is available for download on the notes page of my website. This is Part 2, the scientific revolution. Beyond the economic and political upheaval discussed in Part 1 of this lecture, the Renaissance would witness 3 revolutions in thought that would turn the medieval worldview inside out. It would begin with the scientific or astronomical revolution, caused in part by the quest for a more accurate calendar for the Catholic Church. The geographical revolution would simultaneously transform the European understanding of the physical world, and the theological revolution would forever transform the European understanding of religion. This lecture will focus on the scientific, or if you prefer, the astronomical revolution, sometimes called the Copernican shift. This revolution in astronomy would cause a wholesale rejection of Aristotelianism. It's important to keep in mind that for the latter part of the Middle Ages, it was Aristotle that served as the intellectual framework for knowledge, both secular and sacred. St. Thomas Aquinas' 13th century synthesis of Aristotelianism and Christianity provided a powerful interpretive model combining systematic philosophical reasoning with Orthodox Christian theology, just as St. Augustine's synthesis of Neoplatonism and Christianity had done in the late Roman period. If you had a question about the world, the answer was provided by Aristotle's common sense philosophy, or by special revelation mediated through the Church. And thanks to St. Thomas's work, it was thought that there was no inconsistency between these two systems. Copernicus's revolutionary hypothesis of heliocentricity would be advanced by the astronomical observations of Galileo Galilei, made possible by the newly improved refracting telescope. But beyond confirming Copernicus, Galileo's work served to establish empirical observation as a central tenet of science in the coming modern age. We'll conclude Part 2 of this lecture with an overview of Johannes Kepler's insights into the nature of planetary motion, and discover how his work would forever bring to an end the a priori approach to scientific knowledge that had been championed by Aristotle. St. Thomas's synthesis of Aristotle's philosophy and Christian theology had ruled the intellectual world for the last 3 centuries of the medieval period. But the perpetually nagging problem of determining the date of Easter, the most important holy date of the Christian calendar, would bring all of this to a very messy end. To understand the problem, we need to understand 3 things. First, what's the controversy about the celebration of Easter in medieval Catholicism? Second, what exactly is a calendar? And third, why does the medieval calendar need to be fixed in the first place? Without going into all the minutiae of the Quartodecimanian heresy, let's just say that since at least the 2nd century of the Common Era, Christians had significant disagreements about when to celebrate Easter, the date of Jesus' resurrection. The authors of the Synoptic Gospels, Matthew, Mark, and Luke, had used the traditional Jewish dating system based on a lunar calendar to date Jesus' death and resurrection. But the new Christian religion that emerged in the century after Jesus preferred to identify itself with the Roman Empire as a whole, rather than the Jewish province of Judea. Thus, they adopted the imperial solar calendar, which had problems of its own, which we'll go into in a moment. Calculating the differences between the Jewish lunar calendar and the imperial solar calendars led different bishops in different regions of the empire to fix the celebration of Easter on different dates. The First Council of Nicaea further complicated the matter in the 4th century by mandating that Easter be celebrated on a Sunday, which by that time had become the primary day of Christian worship, regardless of the date of the month on which Easter actually fell. Add to that the continuing struggle of the bishops of Rome to superimpose their authority over other bishops of the Church, and the linguistic and cultural struggles that ensued when Constantinople became the capital of the Roman Empire, now known as the Byzantine Empire, starting around 324 of the Common Age, and the general decline in literacy and numeracy that accompanied the collapse of the western half of the Roman Empire in the 5th century. And what you get is one big old mess. By the mid-7th century, at the Synod of Whitby, the Celtic Church, the last holdout for an alternative dating of Easter among otherwise Orthodox Latin Christians, finally accepted what was called the Alexandrian Comptus, and a general consensus of dating Easter was achieved. Never mind that the Irish mathematicians were probably more competent than their Mediterranean brothers. Consensus was consensus, at least in the West. The eastern half of the Roman Empire, now referred to by historians as the Byzantine Empire, completely ignored the Western consensus, and the Orthodox churches of the East celebrate Easter on a completely different calendar than the Latin or Western churches to this very day. But that's another story altogether. So for the purposes of this lecture, let's just say that for a very long time, a lot of people argued about the date of Easter, and when consensus was finally achieved, no one wanted to rock the boat for fear of starting the debate all over again. But even though everybody, at least in the Latin Church, agreed on a single method for computing the date of Easter, when they actually got around to running the numbers and setting the date on the calendar, our second problem occurred. If you've never stopped to think about it, a calendar is just a kind of clock. It tells us what time it is. Not in seconds or minutes or hours, but rather in days, months, years, decades, centuries, even millennia. A clock is a device we use to measure the passage of time on the scale of a single day. But a calendar is a device we use to measure the passage of time on a cosmic scale. A calendar tells us where the heavenly bodies, the hour, minute, and second hands on our cosmic clock, will be at any given time in the future. And just like a regular clock, a calendar is useful in direct proportion to its accuracy. And that was the problem that the church struggled with in the Renaissance. The Julian calendar that was supposed to enable the church to predict when Easter would happen in the future was, like a crappy wristwatch, not keeping very good time. They found that every so often they had to reset the whole calendar to keep it in sync with the position of the heavenly bodies, which could be observed with the naked eye. This brings us to the core of the problem. Why was the medieval calendar so inaccurate? And what, if anything, could be done about it? To understand why the medieval calendar was inaccurate when projecting dates further and further into the future, we have to understand that it rested on Aristotle's model of physics and Claudius Ptolemy's model of astronomy. According to Aristotle, the motion of any body is determined by its substance. The nature of the substance dictates how that substance, or an object made from it, will move. Earthly or terrestrial bodies are composed of the 4 terrestrial elements: earth, water, air, and fire. Aristotle's periodic table was much simpler than ours. Now, the nature of these 4 terrestrial elements is to be temporal and movable. Thus, earthly substances can either be in motion or at rest. Their natural state would be at rest, so if a body is in motion, it's moving toward its natural state. A body already at rest will remain in that natural state unless it's disturbed by some outside force. Also, the terrestrial substances are distinguished from one another by their densities. Earth is the densest or heaviest substance, followed by water, then air, and finally fire, the lightest of the elements. So, if we could separate the elements out from one another, they would naturally form 4 concentric spheres, with earth stuff forming the innermost sphere, surrounded by a sphere of water, which in turn would be surrounded by a sphere of air, which would finally be surrounded by a sphere of fire. Here we see an example of the 4 elements separated into their distinct spheres. In light of all of this, we can say that terrestrial motion, according to Aristotle, is always going to be straight-line motion. It would always have a beginning, and it will always have an end. Any object in motion on Earth will first have to be set in motion, for example, picking up a rock and throwing it, and then it will naturally seek the shortest route to its natural place in the universe. That is, it will move in a straight line toward its home. But in the heavenly realm, things move in a very different way. The heavenly or celestial bodies, the sun, the moon, planets, and stars, are not made of the four terrestrial elements. Being heavenly bodies, divine bodies, they must be composed of a celestial, divine substance. This is the fifth element, ether. Ethereal substance, like terrestrial substance, is movable, but unlike terrestrial substance, it's eternal, without a beginning or an end. Hence, the motion of the ethereal bodies of the celestial realm is, according to Aristotle, circular motion, without beginning or end. Thus, according to Aristotle's physics, the Earth, being composed of the heaviest elements, must be at the center of the universe, with the Moon, Mercury, Sun, Mars, Jupiter, and Saturn, and finally the fixed stars, rotating around the fixed Earth because they're composed of the lighter ethereal element. Now, you might wonder why the celestial bodies in Aristotle's system are not all fixed on the same sphere, since they're all made of the same perfect heavenly substance. But as everyone who has ever looked closely at a heavenly body knows, some of those heavenly bodies wander around in the sky, while the constellations do not. This observation is what astronomers call retrograde motion. That is, some bodies in the heavens seem to move forward, then backward, then forward again against the backdrop of the fixed stars. This wandering motion caused the Greeks to name these bodies planets, literally wandering stars. The sun moved in a very different, though still eccentric way, getting closer and then further away from the Earth at different times of the year we call seasons. This odd behavior of the planets and sun didn't seem to obey the laws of motion dictated by Aristotle's physics. Thus, he concluded that the heavenly spheres must have different spatial locations in the heavens. They must be separate from one another. To account for the seemingly erratic behavior of the planets, Claudius Ptolemy proposed the epicyclic hypothesis. This hypothesis held that the planets moved on a sub-orbit around the Earth called an epicycle. As the planets moved around on their epicycle, it appears from our point of view that it's moving backward and forward as it rotates around its axis, which forms its circular orbit around the Earth. To account for the odd behavior of the sun, Ptolemy proposed what's called the eccentric hypothesis. The eccentric hypothesis held that the deferent, or radius of the sun's orbit, is not directly centered on the Earth, but rather at a short distance from the Earth. This accounts for the sun seemingly moving closer and further away from the Earth during winter and summer. So combining Aristotle's physics together with Ptolemy's synthesis of observed motions of the heavenly bodies, we get the geocentric, or Earth-centered, picture of the cosmos. Now, in order to get all the celestial bodies in the right place at the right time, to also match our observations, requires some 40 different epicyclic or eccentric orbits. Now, the nice thing about Ptolemy's system is that it worked. His model could indeed account for all of our observations about the movements of the heavenly bodies, and it didn't violate Aristotle's laws of motion, which everybody just knew, and indeed, which common sense seemed to confirm, was correct. The problem with Ptolemy's system was the amount of calculations required to predict all the epicycles and eccentric orbits of the heavenly bodies. Let's just say it was a lot of math. And Ptolemy was doing these calculations using the whole numbers of the Roman mathematical system, since zero and decimals had yet to make their way into the West. Needless to say, the further you calculated into the future to build your calendar, the more errors began to creep into the system. Thus, over time, the calendar became less and less accurate. And this is the problem that Nicholas Copernicus was trying to resolve. But after carefully studying both Aristotle and Ptolemy, he concluded that the geocentric system really was the best possible synthesis of both Aristotle's physics and our ordinary observations of the retrograde motion of the planets. However, if one were to change the initial assumptions about the motions of bodies, that is, if one were to ignore Aristotle's explanation of why bodies move the way they do, And if one were to place the sun at the center of the cosmos instead of the Earth, one would eliminate the need for Ptolemy's eccentric orbits and epicycles. Adopting a heliocentric or sun-centered model of the heavens got rid of all that extra math. And, according to Occam's razor, we should never unnecessarily multiply our hypotheses. That is, don't make things more difficult than they have to be. So the heliocentric model had a lot to offer those who were interested in making calendars. Unfortunately, the heliocentric model not only contradicted Aristotle, it also contradicted the Bible, the church, and common sense experience. So while it might be good for calendar makers, it was obviously just plain wrong. After all, if Aristotle was wrong, then our common sense experience is wrong. And since there are passages in the Hebrew Bible that confirm Aristotle and common sense that the sun moves around the earth, it was practically inconceivable that Ptolemy's model might be incorrect. One side note before we move on, and that is, despite what you've learned in high school, Copernicus did not invent the heliocentric model. It was actually first proposed by Aristarchus of Samos, 100 years after Aristotle, but nobody took his model seriously since it ran counter to the established authority of both Aristotle and common sense. Now, you might think that Copernicus's bold objection to the standard geocentric model of the cosmos would land him in big trouble. After all, in denying Aristotle, he's denying the Bible. And in denying the Bible, he's denying the authority of the church. And denying the authority of church means denying the authority of the Pope. And doing that will get you excommunicated. Getting excommunicated from the church means that you go to hell or at least to purgatory, neither of which are desirable outcomes. So you might imagine that Copernicus kept his beliefs to himself so that the church would never find out about his blasphemies. Well, you might think all that, but you'd actually be wrong. The fact is, Copernicus was well aware of the implications of his view, and he went out of his way to emphasize that what he was proposing was only a mathematical model, and that it should in no way be taken to represent any real threat to what we all know to be true through our own experience, let alone what's confirmed by the authority of Aristotle and the Church. That is, that the Earth is the stationary center of the universe. And if you thought that even that would be too inflammatory for the Church, you'd be wrong again. They were only too happy to apply the heliocentric model in order to secure a more accurate calendar so people would know when to celebrate Easter, just so long as everybody was clear that this was only a model. To be sure, there were some who found his proposal just too outlandish, but the church hierarchy embraced the compromise, and almost everyone was happy. They were happy, that is, until Galileo got involved. Now, another thing you probably learned in school was how Galileo invented the telescope and then went on to invent science and single-handedly saved us from medievalism. And once again, what you've learned was wrong. Although, to be fair, he does seem to have started the trend of going by one's first name. Everybody calls him Galileo, and no one calls Copernicus Nick. So I guess he's got that going for him. But, as I was saying, Galileo didn't actually invent the telescope. He did, however, dramatically improve on the already existing idea. He then made lots of copies of his newly improved telescope and sold them. He thus became wealthy enough to retire and spend the rest of his life playing with his little invention. Galileo's improvements to the refracting telescope centered on the accuracy with which he grounded the lenses. He did it far better than anybody else had before. He also worked out the optimal distances between the new, more accurate lenses and the focal point of the light in the tube. This significantly improved the refracting power of telescopes, and, as I said before, allowed him to sell them to merchants who were more interested in looking through them at ships in the Mediterranean in order to fix prices in the markets and get the drop on their competitors. But we're getting ahead of ourselves in the story. So after Galileo had improved the telescope, made his IPO, or at least the Renaissance equivalent thereof, he sat back and pointed his little toy in the one place he shouldn't have. Not the neighbor's window, though he may have done that as well, but up. Up into Aristotle's celestial realm. Up into the divine world of ether. Up into the world of the gods. And what he saw up there blew him away. Let's start with the moon. Well, For something that's supposed to be made of a divine substance, for something that's part of the perfect, eternal, celestial realm, it looked, well, terrestrial. He saw mountains, he saw valleys, and craters, and highlands, and lowlands, which, though quite desertified, looked downright ordinary. And speaking of imperfections, in a realm that's not supposed to have any, when he looked at the sun, he found it had spots. Spots! It's scarred and pockmarked like someone who had survived smallpox or the plague. Jupiter was also downright un-Aristotelian. It had its own moons, and that's just not right. Everything is supposed to be a satellite of the Earth. Aristotle had said so, and Ptolemy had shown how. Besides, the Bible made it clear. The Earth is the center of God's attention. And if planets like Jupiter could have their own moons, well, the whole cosmos seemed to be coming apart. But the killer observation, the one that changed everything and left no doubt in his mind that, in fact, Copernicus had been right, and Aristotle, the Bible, St. Thomas, and the whole damn medieval system wrong, was the way Venus waxed and waned. Now, the waxing and waning of the moon had been observed since humans became conscious, and it had long been understood that the shadow that passed over the moon was caused by the relative location of the Earth, moon, and sun. No problem. But when Galileo tried to position Venus, the Earth, and the sun as it waxed and waned, well, it just wouldn't fit on the geocentric model. There was just no way on Ptolemy's model to account for the plain fact of the observations he was making. Here was new observable evidence that broke in favor of Copernicus and against Ptolemy. When he published his findings and went on tour to promote his book, things got a little hairy. To be fair, the church didn't just send in the Inquisition to break his kneecaps. They gave him fair warning that he was contradicting the teachings of the church, and that they would really appreciate it if he would not be quite so bold in his pronouncements about the inaccuracies of Aristotle, the church, and in particular the Bible. But when he refused to relent, he was invited for a tour of the Vatican, which, for people like him, ended in the basement. He was forced to recant his position. His book was placed on the index of inappropriate literature written by very naughty people, and he was confined under house arrest. He died shortly thereafter. And even though the church hired media consultants to create an ad campaign to discredit the uppity man, who had quickly become known simply as Galileo, once the cat tasted that sweet catnip of liberty outside the bag, there was just no putting it back in again. Copernican heliocentricity was on the ascendancy, and it would be a rearguard action for the church from this point forward. We should note that there were other cosmic models floating around in the chatter that was the Renaissance version of the internet. Martinus Capella had proposed a hybrid geocentric model in the 5th century, just as the western half of the Roman Empire was descending into the giant chaotic mess of the early Middle Ages. More recently, Tycho Brahe, who turned out to be not much better at theoretical astronomy than at dueling, had proposed a synthesis of Copernicus and Ptolemy, referred to as the Tychonic system, which didn't work much better than Capella's. But Brahe was good at making careful observations, like the supernova of 1572. He spent a lot of time at night looking up at the stars, perhaps because he couldn't get dates, which, despite his nobility and great wealth, was probably due to the fact that his nose had been cut off in a duel at college. So whether it was because he was naturally boring, or due to his unfortunate loss, he had lots of time, undisturbed, to record his observations of celestial bodies. He also had the good fortune to recognize talent when he saw it, and he hired a young man, Johannes Kepler, to be his assistant. When he died, Kepler would inherit all of Brahe's elaborate notes, and from them he would work out the last piece of the astronomical puzzle, which would also prove to be the last nail in Aristotle's coffin. You see, even though Galileo had provided sufficient evidence to persuade the unbiased that Copernicus's heliocentric model was not just simpler than Ptolemy's, but also turned out to be more accurate, there were lingering problems. But the most stubborn was the seeming alteration of the velocity of the planets. If the planets were moving in circular orbits, as Aristotle said they had to, then there was no reason for them to change their velocity. But Kepler, applying his basic geometry, worked it out. If the planets were moving on elliptical orbits rather than circular orbits, they would appear to move faster when closer to the Earth and slower when further away, although they were in fact moving at pretty constant speeds. Thus, Kepler formulated the first law of planetary motion, that all planetary motion is elliptical motion. It was now official. Aristotle was wrong. There was no perfect crystal spheres in the heavens moving in perfect eternal circles around the Earth. And speaking of Earth, it was no longer the center of the universe. We were now just one of the planets, no special cosmic status. And what about our common sense, upon which we had relied for evidence supporting Aristotle's seemingly a priori deductions? Well, that all turned out to be unreliable too, as was St. Thomas, who had synthesized Aristotle in Christianity, and so was the Bible when it claimed that the sun moved round the earth, and so was the Church when it held doctrines that depended upon false biblical passages and Aristotelian authority. The whole damn system had just gone up in flames. The universe had just been turned inside out. Everything we thought we knew about the cosmos for 1,000 years, and our place in it, had come to a very ignoble end. But that's not the end of the story. Things actually got worse from here, as we'll see in part 3 of our online lecture about the Renaissance as the historical background for the modern period. Let's quickly review what we've covered in this lecture. We've seen that the Renaissance is a period of history characterized by social and intellectual upheaval. In this part of the lecture, we've focused on the scientific revolution, which is a revolution in astronomy. It's also referred to as the Copernican Revolution due to Copernicus's rediscovery of the benefits of the heliocentric model of the cosmos. The observations of Galileo and Brahe and Kepler provided further evidence for the heliocentric model and ultimately led to a complete rejection of Aristotelian science. But along with the challenge to Aristotle's authority was a challenge to common sense. After all, we experience the cosmos from a geocentric point of view. We don't feel the Earth moving, and we do see the sun, moon, planets, and stars all orbiting around us. But what seems to be true, according to our common sense experience, is not just under suspicion, as it had been under classical skepticism, it was now just plain wrong. And if we can't trust our own common sense, what can we trust? The scientific revolution of the Renaissance turned the universe inside out. No longer was it possible for us to think of our planet as the center of God's creation. It would only be a matter of time before the same logic would apply in other areas of knowledge as well. The anthropocentricity from which we viewed the universe is now in serious doubt. When you put all this together, you can't help but arrive at some degree of skepticism. When everything you think you know turns out to be wrong, only the most stubborn could avoid some very serious internal reflection.